I'm Steve Waldron for Vector GB, and welcome to my second presentation of today in our Web Live 2020 event. In this presentation, I'm going to explore a little bit more about the functional safety concepts we expect to see in ECUs of the vehicle tomorrow, supporting autonomous driving systems and ADAS systems. Before we look to tomorrow, let's take a little look at the type of software we have in the vehicle today to support functional safety. So, of course, there are many ECUs in the car that are not functional safety related. These we call the QM ECUs, quality managed ECUs, where they don't have to take into consideration ISO 26262. On the other hand, of course, there are many ECUs in the car that need to fulfill functional safety requirements and need to be developed in accordance with ISO 26262. And these ECUs nearly always are what we term fail-safe ECUs. If the ECU software or hardware fails in a catastrophic way and it's unrecoverable, then the ECU is typically powered off and all the outputs are turned off and the ECU is considered to be in a safe state. Let's take a quick example of a power steering ECU. So if your power steering ECU fails, and it fails in a way that is not recoverable, then the power steering ECU shuts down, all the outputs turn off, your steering goes very heavy in the car, you get a warning light on the dashboard, a steering warning light pops up, but the driver has the opportunity to pull the car over to the side of the road. Now, of course, that is an undesirable state for the ECU in the car to be in, but it's considered to be a safe state. The driver has the chance to take over control. So, always in these fail-safe scenarios, we always consider that the driver is able to take control of the vehicle in a safe manner, in a safe way. And that sort of concept is perfectly acceptable up until about SAE automated driving level 2. Once we move beyond that, then the driver is considered not to be in the loop anymore, and we need to take some additional considerations. But before we look at what we need to do to meet driver levels 3 and above, let's take a little bit more of a look in what we typically do in these fail-safe scenarios. So when we have something like a power steering ECU or a braking ECU, these are typically developed to the highest automotive safety integrity level, ASIL D. And very often it's desirable to try to attempt to make all the software inside that ECU all ASIL D, as is shown here on this example in ECU 4. But in reality, that's really quite difficult to achieve. And so what we end up in reality is often a mix of quality of software inside the ECU. So, for example, in your power steering example, the power steering application might be developed according to ASIL D, but the UDS diagnostic stack inside, which is rather a substantially large piece of software, the UDS software doesn't have any functional safety requirements. So that diagnostic stack might only be developed according to a QM process. And then beneath the application, right at the bottom layer, you have the driver level, often called the MCAL in AUTOSAR. And that MCAL might only be available according to QM or perhaps ASIL B, even within your ASIL D application. So typically in an ECU, we see this mix of QM software and ASIL software. And so we have to be able to support that. And the way we support that in ISO 26262 is with a concept called freedom from interference. Freedom from interference means that if the QM software has a fault that we haven't discovered because it hasn't been through the rigor of the ISO 26262 development process, then that QM software will not instigate a safety-related fault into the ASIL software. So this means that the ASIL software can operate free from interference from any faults in the QM software. Now, there are a number of different mechanisms that we use to ensure this concept of freedom from interference. The first mechanism we use is a concept called memory protection. And memory protection means that the QM software will not instigate any memory or spatial faults in the ASIL software. So, for example, as the QM software runs and it has a rogue pointer in it, and because we haven't peer-reviewed that QM software to a level of rigor demanded by ISO 26262, that row pointer writes over the stack in the ASIL software. So that's a memory violation. Now, memory protection is offered within the AUTOSAR operating system at Scalability Class 3 and Scalability Class 4. And memory protection means that the MPU, the Memory Protection Unit, is configured to detect these types of memory violations. If the QM software writes into the ASIL software, then that memory violation is detected by the operating system. So what happens is we set up what we call contexts. The QM software runs in what's termed a non-trusted context. This means it's allowed to access a restricted memory space. And the ASIL software is what we call trusted, and that means it can access all the memory space. And if your non-trusted software touches any memory outside into the region in which it's not allowed, then the MPU trap will be handled by the operating system. So that's memory protection, and that's one of our key cornerstones, if you like, for the freedom from interference. Our second cornerstone is timing protection. And timing protection means that we give the ASIL software, the safety-related software, that we ensure that it starts on time and that it's given enough runtime. So let's take another example. We have an infinite loop within the QM software, and this infinite loop hasn't been detected because we haven't gone through our necessary level of testing and quality rigor that we would have normally done for ASIL software. What we don't want to happen is that the infinite loop in the QM software starves the ASIL software from the necessary runtime. So we need to provide some form of timing protection. Now, timing protection can be provided by the operating system, and specifically operating system scalability class 2 or scalability class 4. But actually we don't tend to use the operating system for this level of protection for a number of different reasons. For timing protection, we tend to use the AUTOSAR Watchdog manager, Watchdog mechanisms. There's a number of different advantages with the Watchdog in AUTOSAR. So the Watchdog in AUTOSAR is what we call a window watchdog. This means that we can detect that a task has started on time and that it's given enough runtime and that it also ends on time. But not only that, the Watchdog offers another feature, and that's called program flow monitoring. And program flow monitoring means that we can set up a number of different checkpoints in the safety-related parts of the software, and we can check that we've hit those checkpoints not only within the correct window of time, but also in the correct order. And so if the QM software starves the safety-related software of the necessary runtime, then a Watchdog event occurs and the ECU is pulled into a safe state. So that's timing protection. So we have memory protection and we have timing protection. And then finally, our final concept in this overall concept of freedom from interference is data protection. And data protection means that when we send data in and out of software components and software tasks, that we can detect if that data has been corrupted. And in this example here, we're using messages on a CAN bus. So, for example, a message can be transmitted on the CAN bus and it's safety-related data, and we want to ensure that it hasn't become corrupted. Well, what we do with AUTOSAR mechanisms is we append a CRC and a rolling counter to that data using a mechanism we call end-to-end protection. And the CRC is used to detect if any data has become corrupted, and the rolling count is used to detect that all the messages are received and received in the right order and that we haven't dropped any messages. Okay, so end-to-end protection is used to ensure data integrity. So we have these three main mechanisms: memory protection, timing protection and data protection, and these mechanisms are used to build up our freedom from interference argument to show that the trusted software can operate free from interference from the non-trusted software. And if any catastrophic error was to occur, or for example if a Watchdog event occurs due to timing protection, or if we lose a number of different messages on the bus that arrive corrupted, then we can take our safe state handling, and often as I mentioned before, this safe state handling is to put the ECU into an off state, undesirable but considered safe. Now, autonomous driving systems and ADAS systems, as soon as we take the driver out of the loop and we can't rely on falling back on the driver anymore, and this especially means the higher SAE driving levels, then we need a more robust level of rigor. And this is what we term fail operational software. Fail operational software, which goes well above and beyond our normal fail-safe software, means that so first of all, we have to take into consideration that it's impossible to avoid every fault completely. And once we have that into consideration, then fail operational software means that either we must avoid all the faults wherever possible, most preferred approach, or any faults that we do encounter must be tolerable and we must recover from them. So we must have, for example, a graceful degradation method where the ADAS function, the driver level function, must be maintained even in the presence of faults in the hardware or in the software. And in this mechanism, the driver is intentionally not a fallback. So we have to either rely on additional software or additional hardware mechanisms in the event of faults, but we can't rely on the driver anymore. When we take a look at specifically Vector's basic software that we provide, our AutoSAR basic software, typically we have to develop our basic software with some generic safety goals in mind, and fail-safe software is typically developed with the safety goal ensuring the integrity of the function. Ensuring the integrity of the function means essentially our freedom from interference concepts. We check that data has not become corrupted when it comes in and out of our software function. We check that the function is given enough runtime. We check that any QM software has not disturbed our memory, our spatial area from the safety related function. So what we're actually doing is ensuring that integrity of the function. But if that function doesn't run due to any of these faults, then the whole system fails in a safe way. In fail operational software, we have to go above and beyond this. It's not adequate just to ensure the integrity of the function, but now we actually have to ensure the availability of the function. Availability of the function means we need to make sure that that software can always run to a level of rigor determined by the ASIL-D failure rates. So this is a new level of requirement. Availability is a new level of requirement above and beyond what we would have had to normally meet for fail-safe systems. When we take a look to the hardware necessary to support this fail operational, then this is a typical fail-safe system that we would have in place today. We have a sensor, we have a microcontroller doing all the processing of the software, and we have an actuator. And we have our external watchdog here in this diagram that would handle the watchdog resets. Now, if a sensor fails, then the whole system can be shut down, the actuators can be shut off. If the actuators fail, then we can shut the system down. And if the software goes wrong in any catastrophic way, then we can use the watchdog to turn the power off to the system. We can cut the power supply to the system, but the system fails in a safe way. And if any hardware faults occur, the system can fail in a safe way. Now we need to move to fail operational. And fail operational means we have to either avoid these faults or we have to tolerate these faults. And toleration of the faults means that, for example, if a sensor fails, we need to fall over to a backup sensor. If an actuator fails, we need to have a backup actuator in place. And this means now the inclusion of a redundant system. So this is has been until now uncommon in automotive systems due to the cost impact. But today with our fail operational systems, we see more and more hardware redundancy built into place. And this means if sensor number 1 fails, we can move over to sensor number 2. If actuator number 2 fails, we can move back to actuator number 1, and so on and so forth. So we have genuinely 2 channels here with redundant systems. So hardware, of course, is exposed to random hardware faults, and we can talk about the bathtub curve and wear-in failures and wear-out failures, but typically what we would see in hardware is if a sensor goes wrong on channel 1, then we would fall over to channel 2, and perhaps the channel 2 sensor would fail eventually, but we have a redundant channel that can take over. Now, these redundant channels address random hardware failures, but they don't address systematic or common cause failures. So if we're exposed to a common cause failure that occurs both on channel 1 and channel 2, then both channels can fail in the same at the same time in the same way. Now, software, by its very nature, has systematic faults, are systematic faults inside, and so this means if a piece of software that's processing is exposed to the same inputs and gives a wrong output, if you have a second piece of software doing the same processing, given the same inputs, it will give the same output. And so software by its very nature is exposed to these common cause failures. Finally, we have the problem of a latent fault, and a latent fault means that it can be a systematic fault, but it can be a systematic fault that only occurs given a certain set of inputs. So this can also occur in software, because if the software is being processed on channel 1 and has a set of inputs that leads to a fault, when channel 2 takes over and is given the same set of inputs, eventually channel 2 will fail in the same way. So this is quite a problematic level of systematic fault called a latent fault. And these are exactly the types of faults that we want to avoid or tolerate with graceful degradation in our software. Okay, so ISO 26262 gives us some guidance when it comes to fault tolerance and fault avoidance. So fault tolerance basically means that we use a number of techniques to keep the software operational despite faults already being present in the software. And when it comes to hardware, this means redundant hardware, but when it comes to software, this would typically also imply redundant software mechanisms. So when we look at AutoSAR basic software, this would probably mean using 2 different sets of AutoSAR basic software on the 2 different channels. And this really becomes economically infeasible for most projects. So the other approach that ISO 26262 suggests is methods for fault avoidance, and this means reducing those systematic faults by developing your software in accordance with ISO 26262 Part 6, the software development standard. And this is our preferred approach, to avoid those faults by developing our software to a necessary level of rigor. So let's see what actually that means inside our software. What level of extra rigor do we have to go to? Well, when we look at our basic software, first of all, this means more software will get safety requirements allocated. So we have this new top-level functional safety goal regarding availability of the software. And of course, we need to place software safety requirements in place to ensure the availability of that software. So we have brand new safety requirements that we never had before. When we look at the existing requirements that we have, more of those requirements become safety related. So the AutoSAR standards provide us with many hundreds of thousands of requirements, and it means some of those will now become safety related, whereas before they were only functional requirements, now they become safety related requirements with a necessary ASIL. When we delve into the actual design of the software, this means we have smaller software units and no data sharing between units. So the units become smaller and we're not permitted anymore to share the same data between units, for example, with the use of global variables. And we need to ensure that the software has been tested at the unit level and also tested at the component level in a very, very robust way. So you can see that through our development process, we have to meet much more rigor for fail operational software than we had to in the past. Now, there are 2 ways that we can really show fault avoidance through the ISO 26262 development process. First of all, is to use cleanly developed code. This means essentially write the code from scratch and write the code according to ISO 26.26.2 Part 6 and strictly follow the design and testing requirements from the process. But of course, we have a large bulk of AutoSAR software that has been under development for 10 years, and that's what we call our legacy code. And it's really quite difficult to develop large amounts of those legacy code clean from scratch again. So we need another method. And that other method is to show confidence in our test suite that we have a comprehensive enough suite of tests to thoroughly test those requirements, even if some of the design and the test aspects are legacy. And by using a combination of these two approaches, cleanly developed code and comprehensive test suites for legacy code, we want to show and provide enough evidence that we have fault avoidance up to a level of rigor expected of ISO 26262 ASIL-D. Let's take a quick look at those two methods in a bit more detail. So I've already spoken about cleanly developed code. This means smaller units, low complexity of that code, no sharing of data between those units, so those data units only operate on data of their own, and really robust testing at the unit level and all the component level. So we really develop that code at a small, low complexity level from scratch through the ISO 26262 process. This is our preferred way of arguing fault avoidance for a component. But of course, as I mentioned, we have a lot of legacy code, and legacy code we also have to reach this fail operational level. And this means showing that we have a robust test suite, robust enough to test the requirements and the design, showing 100% CDC coverage level, to a level of rigor that would be expected of ISO 26262 ASIL-D. Now, it's important to note this is not a proven in use argument. We're not attempting to use an argument that says we have this software in production for many hundreds of projects for many, many years. This is not that type of argument. This is an identification that we have a very thorough test suite to show that our software meets the level of requirement and design necessary for ISO 26262. And we use this method where, in fact, the code base has been established for a long time, and actually we expect that if we had to refactor the code or rewrite the code according to the ISO process, then that refactoring of the code would actually introduce more risk into that code than bolstering our test suite. Okay, so that's it from me today. For conclusions, AutoSAR Classic that we have in place today is a well-established solution and has been using this fail-safe mechanisms with operating system, memory protection, watchdog timing protection, and data protection using end-to-end protection mechanisms. And those freedom from interference mechanisms have allowed us to build fail-safe ECUs, which are suitable up to ADAS level 3. But if we want to move, beyond ADAS level 3, and beyond, then we need a new generation of safe software, and this means fail operational software where we avoid faults in the software and the driver is not in the loop anymore. Okay, I hope you've enjoyed this talk, and I'll welcome any questions you might have.